cubic satellite, or a CubeSat, have been implemented since the early 21st century as a means of educational purpose from institutions around the world. They explore space in ways that full-size satellites cannot. Because of its small size, they're only 10 by 10 by 11 centimetres, they're only a fraction of the cost of full-size satellites. And we have been given the task of designing a CubeSat to test an attitude control device which tests thermal control systems.
In the development of CubeSats, there are a few policies that must be followed. One of them is that the mass of each unit of a CubeSat may not exceed 1.33 kilograms. The total mass lost must be less than 1% of the actual CubeSat. The other and most relevant policy is that a CubeSat may not store more than 100 watt-hours of energy, which is why we look into thermal control as a means of attitude adjustment.
So I've been researching drag and looking at the atmosphere because that dictates the orbit that we're going to have, and depending on our altitude from the Earth, we will be in a different part of the Earth's atmosphere. So if we're in a low Earth orbit, we'll be looking at between 50 to 600 kilometers, and it turns out that the coefficient of drag is actually still quite strong there. So I've been looking at how to model this and create a simulation which allows us to calculate the forces on the different faces that we can then use to see whether the system that we're going to use to control its attitude is going to be able to create powerful enough torques. In a low Earth orbit, the density is so great that actually the control system we're looking at using wouldn't be able to create a powerful enough torque, so it turns out we probably have to go to a higher altitude in order to use that system.
As Simon has mentioned before, lower Earth orbit is not possible for us because drag is too strong. Therefore, I looked in geostationary orbits and realized there's a lot of hazards that could endanger the mission of our satellites. Some of the hazards can cause our orientation of the satellite to work badly, so our star tracker can show the wrong orientation, or for example, discharge can happen and electronics just fail to work. So we need to find mitigation methods to prevent these effects on our satellites.
One of my tasks was to measure the attitude determination system of the satellite to the roll pitch and yaw. The aim of the project was to finally manoeuvre the CubeSat, which means that to do this it needs to know precisely where it is. The main methods to accomplish this were star tracking, which uses a map of the stars, sun sensing, Earth, nadir or horizon scanning, which uses position above the Earth to determine its orientation, and usually these are used in conjunction with magnetometers, which read the magnetic field around the Earth, and a selection of gyroscopes.
So what we're looking to at the end of the day achieve is that we want two guidance systems that will work hand in hand. So we want a fine control system based on thermal control mechanisms, which is one aspect of our project, but also these magnitudes aren't going to be large enough to control against certain fluctuations and noise considerations for the satellite in space. So in order to account for those, we need to use a more powerful system to control the attitude in those instances. So for that, we thought that the use of technology that's already been used in larger satellites, such as the reaction wheel, would be most appropriate. So this reaction wheel can control the attitude to a much greater degree than the fine control system, but then when you really want to get down to the precise measurements, the fine control system is going to get you the whole way there.
One of my jobs was to try and quantify the different effects that the CubeSat will be subjected to in its orbit. And quite a few of them could be dismissed out of hand, like the Yarkovsky effect just being extremely small. But other ones are actually quite significant, like for example, the Earth's magnetic field will cause the CubeSat, if it has a magnetic moment, to align with the magnetic field like a compass needle would. Even things like the difference in gravitational strength of the Earth's gravitational field between one side of the CubeSat and the other will cause it to align and point towards the Earth. And just to give you an example of how precise we are trying to be, we even have to take account of the solar radiation pressure, which is a very, very tiny effect. It's the same as the weight of this 10p coin spread over the area of 27 tennis courts. But that gives you an idea of how precise we're trying to be.
Initially, we started off by looking at what's involved in generating a torque via thermal emission on a satellite. this can be done one of two ways. We adjust either the emissivity of one of the surfaces, or we adjust the surface temperature. Adjusting these properties can give you, on opposing faces, can be used to generate a torque on the satellite to rotate it about one of the axes. This is done by photon pressure, or radiation pressure, as thermal emission occurs from the faces.
My task was to look into communication between our CubeSat and one or multiple ground stations. There are two main types of signals being exchanged, an uplink signal and a downlink one, which, as the name suggests, are respectively the signal being passed from the satellite to the ground station and vice versa. In deciding upon the communication system, many factors needed to be taken into account, primarily the orbit into which our satellite would be. Then there was also the issue of finding a radio frequency band for the signals that would not interfere with many others. Another main point of focus was the thermal control system to be used in order to maintain the CubeSat's temperature within a certain specified range. The system to be used can either be passive or active, both of which were covered in this project. This is important to ensure that there is no large temperature gradient across the strata. This becomes even more so important as our aim is to design a CubeSat that can use thermal control as a means of attitude control.